In today's lesson, we are mastering the concept of the domain of functions. The domain is simply the set of all possible input values for which a function is defined. In your Cambridge IGCSE Additional Mathematics exam, correctly identifying the domain is essential for sketching graphs, finding inverse functions, and solving complex equations. By the end of this session, you will be able to determine the domain for polynomial, rational, square root, logarithmic, exponential, trigonometric, and modulus functions. Let's start with the most straightforward type, polynomial functions. This includes linear, quadratic, and cubic functions. A polynomial is defined for every possible real number. Unless the question explicitly gives you a restriction, the natural domain is always all real numbers. Take the function f of x equals x squared minus 4 times plus 3. Since there are no square roots or denominators to worry about, the domain is simply x is an element of the real numbers. Even for a constant function like f of x equals 2, the domain remains all real numbers because the function exists for every value of x. In IGCSE exams, you will often encounter restricted quadratic functions. A standard quadratic function is not one-to-one because it fails the horizontal line test. To find an inverse function, we must restrict the domain so that it becomes one-to-one. This restriction usually starts from the x-coordinate of the stationary point, also known as the vertex. For this function, the vertex is at 3, 2. By restricting the domain to x is greater than or equal to 3, we only use the right-hand branch of the parabola. This ensures that every y value corresponds to exactly one x value, allowing an inverse function to exist. Next, we examine square root or radical functions. In the real number system, we cannot take the square root of a negative number. Therefore, for any function involving a square root, the expression inside the radical, the radicand, must be non-negative. Let's find the domain of f of x equals the square root of 2x minus 6. We set the inside expression to be greater than or equal to 0. Adding 6 to both sides, we get 2x is greater than or equal to 6. Dividing by 2, we find our domain. The function is only defined when x is 3 or greater. Now let's look at rational functions, also known as reciprocal functions. These are functions where we have one expression divided by another. The fundamental rule here is that division by 0 is undefined. Therefore, the denominator can never equal 0. Consider the function f of x equals 3 over x minus 4. Setting the denominator not equal to 0, we see that x cannot be 4. Visually, this creates a vertical asymptote at x equals 4. The graph approaches this line but never touches it. The domain is all real numbers except 4. What about f of x equals x over x squared minus 1? Here, x squared cannot be 1. This means x cannot be positive 1 or negative 1. The domain is all real numbers excluding plus or minus 1. Logarithmic functions have strict requirements for their arguments. Whether you are using the natural log or log base 10, the argument must always be strictly positive. Unlike square roots, a logarithm cannot even take 0 as an input. It must be greater than 0. Let's look at an example. Find the domain for f of x equals the natural log of x plus 2. By solving the inequality x plus 2 is greater than 0, we find that x must be strictly greater than negative 2. Visually, the domain includes all values to the right of negative 2 on the number line, not including negative 2 itself. In more advanced problems, you might see a variable in the base of the log. In this case, 3 conditions must be met. The argument p of x must be positive, the base q of x must be positive, and the base q of x cannot be 1. Consider example 2. For the function f of x equals log base 1 minus x of x plus 1. First, the argument x plus 1 must be greater than 0, which means x is greater than negative 1. Second, the base 1 minus x must be greater than 0, giving us x is less than 1. Third, the base 1 minus x cannot be equal to 1, which implies x cannot be 0. Combining these three conditions, the domain is the interval between -1 and 1, excluding 0. Exponential functions, such as e to the power of x, are generally very well behaved. The exponential function itself is defined for all real numbers. Therefore, the domain of an exponential function is simply the domain of its exponent. Look at f of x equals 2 to the power of x minus 1. Since the exponent x minus 1 is a polynomial, it is defined for all real values. Remember, the exponential function is the inverse of the natural log, while the domain of e to the x is all real numbers. Notice that its range is restricted to values greater than 0. Now consider g of x equals 5 to the power of 1 over x. Here, the exponent is 1 over x. We know that for 1 over x, the denominator cannot be 0. Therefore, the domain of the entire function is all real numbers except 0. In additional mathematics, you will frequently see trigonometric functions where the domain is already restricted to a specific interval, such as 0 to 2 pi. However, we must also understand their natural domains. The sine and cosine functions are defined for all real values of x. There are no values that cause these functions to break. This means if f of x equals sine of g of x, then the domain of f is simply the domain of g. The tangent function is different. Since tangent x equals sine x over cosine x, it is undefined whenever the denominator, cosine x, is 0. Specifically, f of x is tangent of x is undefined where cosine of x equals 0. This occurs at 90 degrees, 270 degrees, and so on. Let's look at an example. Find the domain of f of x equals cosine of 1 over x minus 1. We know cosine is defined for all inputs, but the input here is a rational function. We cannot divide by 0. So x minus 1 cannot be 0, which means x cannot equal 1. Thus, the domain is all real numbers except 1. Now consider example 2. f of x equals tangent of x minus pi over 3. The domain is all real numbers except where the corresponding cosine function is 0. Identifying these gaps is vital for correctly sketching trigonometric graphs and solving equations. The modulus function, written as vertical bars around an expression, simply takes the absolute value of the output. Because the modulus is applied after the inner function has been evaluated, it does not impose any new restrictions on the input. Therefore, the domain of a modulus function is identical to the domain of the function inside the bars. Let's look at an example. Take the function f of x equals the modulus of 2x minus 5. Since the inner expression 2x minus 5 is a linear polynomial, it is defined for all real numbers. Thus, the domain of f is all real numbers. Now consider a modulus function containing a square root. F of x equals the modulus of the square root of x minus 1 plus 2. Here, we must look at the inner function. The square root requires the radicand to be non-negative. So we set x minus 1 to be greater than or equal to 0, which gives us x is greater than or equal to 1. The modulus doesn't change this requirement. So the domain remains x is greater than or equal to 1. The bars only ensure the final result is positive. They don't help the square root deal with negative inputs. Let's apply everything we've learned to a Cambridge-style question. The function f is defined by f of x equals the natural log of 2x plus 4, all over the square root of 5 minus x. Find the domain of f, giving your answer in interval notation. To solve this, we must satisfy the conditions for both the numerator and the denominator simultaneously. First, look at the natural logarithm in the numerator. The argument 2x plus 4 must be greater than 0. Subtracting 4 and dividing by 2 gives x greater than negative 2. So for the log to be defined, x must be greater than negative 2. Next, look at the denominator. We have a square root, which usually means the inside must be greater than or equal to 0. However, because this square root is in the denominator, it cannot equal 0. Thus, 5 minus x must be strictly greater than 0. Rearranging gives 5 is greater than x, or x is less than 5. Now, we combine these two inequalities. X must be greater than -2 and less than 5. In interval notation, we write this with parentheses to show that the endpoints are not included. When finding the domain, even strong students can make simple errors. Let's look at how to avoid them. A common mistake is treating square roots and logarithms exactly the same. Remember, the square root of 0 is defined, but the log of 0 is not. Don't forget that equal to bar for square roots. Notice what happens when a square root is in the denominator. A student might wrongly write x minus 2 is greater than or equal to 0, but correctly, it must be strictly greater than 0. In this specific case, the equal to bar must be removed because the denominator cannot be 0. When solving inequalities for domains, students often forget to flip the inequality sign when multiplying or dividing by a negative number. Dividing by -2 gives x is less than -3. Failing to flip the sign will lead to an entirely incorrect domain. Always double-check your sign direction. To secure top marks in your additional mathematics exam, keep these professional tips in mind. Always scan the question carefully. Even if a function is naturally defined for all real numbers, the examiner may provide a specific restriction like x is greater than 0. If a restriction is given, that is your domain, regardless of the function type. Be precise with your mathematical notation. If the question asks for the domain in set notation, use curly brackets. If it asks for an inequality, ensure you use the correct symbols. Mixing these up can cost you easy marks. If you are unsure about a domain, especially for modulus or restricted quadratic functions, do a quick sketch. Visualizing where the graph starts, ends, or breaks can help you spot vertical asymptotes or stationary points that define the domain boundaries. Always test the boundary values of your domain. Plug them back into the original function. If the function becomes undefined, like getting a 0 in a denominator, you know that specific endpoint should be excluded using a strictly greater than or less than sign. It is time to test your understanding. Please pause the video and solve these 3 questions before continuing. The easy question asks you to find the domain of f of x equals the square root of 4x minus 12. The medium question is to state the domain of g of x equals 5 over x squared minus 9. And the hard question, find the domain of h of x equals the natural log of x plus 5, all divided by the square root of 10 minus 2x. Take a moment to work through these carefully. Let's go through the homework solutions. For the square root, the expression inside must be greater than or equal to 0. Adding 12 and dividing by 4 gives x is greater than or equal to 3. For the rational function, the denominator x squared minus 9 cannot be 0. This means x squared cannot be 9, so x cannot be plus or minus 3. For the hard question, we have 2 conditions. The log argument must be positive, and the square root radicand must be strictly positive since it is in the denominator. Combining these, the domain is x between -5 and 5.